Hi everybody. Today I am going to discuss about singly reinforced beam with tension steel yielding. So this is the case where failure is initiated by yield of the tension reinforcement. But for the less desirable case where the concrete crashes in compression before tension reinforcement yields. But we are not going for that case. Our case is failure is initiated by yield of the tension reinforcement. Now, the basic design equation for flexure, it is factored resistance greater than equal to effect of factored loads. In notation, we can write MR greater than equal to MF. We can see it here. So this MF, it is the moment due to factored loads, effect of factored loads, as I have written like that. So, and the term MR, it refers to factored moment resistance of the cross section. So here the resistance, this word, it implies strength, and it is calculated using resistance factor phi c and phi s to reduce the specified strength of concrete and reinforcement. That's the reason we are using this. Now the question is, why the resistance factors we are using? Basically to account for possible variations of dimension of the cross section, or for possible variations of material strength, and also for possible uncertainties in the strength equations. Now here I have taken a beam section. It is rectangular cross section with width B and effective depth is D. And this beam, this section from the beam, it is taken, and that beam is considered to be properly reinforced. That is, it fails in steel controlled mode. That's what I told at the beginning, tension steel yielding. Now, this equilibrium of forces acting on the cross section, here we can see this is typical cross section, and this one, it is isometric view of stress distribution. And one important thing here, we can see there is force couple CR and TR. So regarding this, we shall see in details in the next slide. As you understand, the internal bending moment developed at any location within a beam, it is resisted by a force couple. As I said, it is CR and TR. And this CR and TR, it is separated by a lever arm JD. We can see here. And also we can see there is resultant concrete compression force. It is CR equal to this part, it is taken from here. And because this is a stress block, concrete compression, this stress block, height is A, and top fiber distance from neutral axis is C. So A, it is fraction of C, and it is represented by A equal to beta 1C. That's why when we calculated the resultant concrete compression force, it is equal to actually product of area of the compressive zone of depth A and width B. This one here, it is very clear. Depth is A, width is B. So AB is the area, and this part, it is uniform stress of magnitude. We can see here phi C alpha 1 F prime C. So this stress multiplied by A B will get this. As I said, A equal to beta 1 C, so it is written beta 1 C. Now the tension force in the reinforcement TR, it is equal to product of the factored stresses in steel, that is phi S Fy. Then this will be multiplied with AS, reinforcement area. So we get tension force in the reinforcement. We can see it here, how it is shown. Now these two forces, CR and TR, couple of forces which is separated by JD, lever arm, we need to use equilibrium of forces. How to do that? Let's see. So using equilibrium of forces acting on the cross section, we can compute A. So for equilibrium, we can write CR equal to TR. So we know CR and TR, already we have seen in previous slide. This comes from CR, this comes from TR, so easily we can find A. A is the stress block height, A. So let's see in the next slide how to use this A, as well how to check the Fs equal to Fy. As I said, determination of whether Fs equal to Fy. So what to do? Here it is a strain diagram. The balance condition we can see here. This is the balance condition. This red line, the strain distribution diagram, this red line is the balance failure one, and the balance condition normally it is characterized by simultaneous crushing of concrete and yielding of tension reinforcement. Very important point to understand. Simultaneous crushing of concrete and yielding of tension reinforcement. The strain in the concrete we can see at the top, because this is concrete part, compression zone. So the strain in the concrete reaches maximum value F sum Cu equal to 0.0035, while the strain in the steel, it reaches the yield strain. It means epsilon S equal to epsilon Y. This is yield strain. Consequently, the stress in the steel, I mean this Fs stress in the steel is equal to the yield stress, that is Fy. So Fs equal to Fy. Now we see that this one, for this case, I put here dotted line, here dotted line. This is the balanced failure one. So this one here indicates reinforcement ratio less than balanced reinforcement ratio. As well, this one epsilon S, stress in the steel, I mean strain in the steel, is greater than yield strain. Strain in the steel greater than yield strain. As well, stress in the steel is equal to yield stress, Fs Fy. This is our condition for getting tension steel yielding. And this one vice versa, exactly opposite. Because this is greater, here it is less. Here Fs equal to Fy, here Fs, stress in steel, is less than yield stress. Strain in steel less than yield strain. But our case is this one. Now, from balance condition, balance failure condition, if we see the triangle, similar triangles, then surely we can write like this. Similarly, we can write like this. Now CB by D, it is balance condition. Epsilon Cu, this one, plus of epsilon Y. So what we will do? We will just substitute epsilon Cu 0.035, but we will multiply above and below by modulus of elasticity of steel, then it gives this value. Very important, because this one 0.0035, if you multiply by this, then it will come 700, and also here 700. This will be Fy. This is our main equation for Cb by D. Now we can substitute Cb by AB, only we need to add right hand side beta 1. So once we are done with this, so our target to see our steel strain, how much? So our steel strain already we have written here, greater than epsilon Y. So epsilon Y means 0.002. So surely our strain will be 0.002425 or 0.003 or 0.004. Always it will be greater than 0.002, as it says here, to get tension steel yielding. This is actually, this side, it is elastic. This is elastic. Steel stress within elastic. So now what you can write? To check whether FSFY, what we need? Of course, A by D must be less than AB by D. So when we will do our example problems, then always we will check our A by D must be less than AB by D. This is balanced one. But the question is, this value most of the time it comes more than 0.5. So our value always will be less than 0.5. Then we are okay. So let's move ahead. Compute the design moment capacity, MR. We know what is MR. So to find the equation for MR, we can use TRJD or we can use CRJD. Same thing. All the parameters what you can see here in equation MR, we know all. We know all already, we know how it comes, and this is lever arm. So for CR also we can write same way, D minus A by 2. Now what we will do, this A, we know the equation of A. So we will substitute the equation value of A here. So let's see. Here another important thing, already in our equation for stress block depth, here it was AS, but I am substituting this with this equation, rho equal to AS by BD. So AS equal to rho BD. So I put here rho BD, B also here in the denominator. So BB gone. So this is the equation for stress block depth A with in terms of rho. Very important point. Now we'll bring MR equation and we'll substitute this value of A. So it will take this form. This is our equation for MR. Now this one except BD square, this remaining part except BD square, we will put a name that is called KR. So let's see that in next slides. So as I said, it will be MR equal to KR BD square. That KR means already we know this full part we are putting term as a KR. So we can write our equation in short form as this one. And KR value, we can find it from the table, it is A3 in CSA A23.3. There is a table. From that table we can get the value of KR for various concrete strength and reinforcement ratio for common case of say Fy equal to 400 MPa. So easily we can get it. And also there is another table, BD square divided by 10 to the power 6. There is another table, and from that table we can get the value for the section sizes B and D from that table. So in my next video I will show how to create that table, both table, and how to solve the problems. So we are done for this part. Thanks for watching.